Alrighty. So figured we'll go through our walkthroughs for homework 4. I'm going to start with problem 3 since 3 comes before 4. Figure that's fairly straightforward. Step 1 with all of these things is to read the entire problem statement. So we're going to be producing the model shown below in SolidWorks and submit our solid part file. First up, our dimensions are in millimeters, so we're going to set our units. MMGS, we're good there. As a reminder, material and part mass are given for us to double check our work. The model is not graded by mass, it's just given for our use as far as making sure that we're not completely off. We're going to follow good modeling practices, no calculating dimensions, no skipping dimensions, no repeating dimensions, and we're going to make sure that all of our sketches are fully defined and that our model matches the given orientation. This problem covers material up to lab 11. And we have 2 hints. So hint 1 is that the helix is best done before the other portions of the composite curve whenever we're doing a complex sweep. This sweep uses a helix and 2 sketches. Each of the sketches will need a separate reference plane. We're going to look for points and axes that the planes pass through and use those to help us define our planes. The second hint is that our main loft has 3 profiles. We have the end surface of the sweep, an arc slot, sketch, which we can see in section A, right there, and an ellipse sketch, which is our removed section off of section B. So this is a section from a section from a section, which you can do, but I'm sure if an actual engineer looked at this, they might scratch their head a little bit as to why I did that. But trust me, this was the easiest way I could get all of these views to fit onto a single drawing. So, all right, let's take a look at our thing and break it down. So we've got sort of this cylindrical puck down at the bottom that is a cylinder. That's going to be fairly straightforward, nice and easy point there. Then we've got a sweep that sort of follows our helix up, and then it's got these 2 elbows. So one of them is defined by the radius 5 we can see in the front view, and the other elbow is defined by the radius 4 we see in section B. So that's going to be our sweep path. We're creating a helix, elbow 1, then elbow 2, then we're going to stitch them all together with a composite curve and a circular profile sweep to get our geometry. The next step is going to be our loft. So we have our first profile already with the ending surface of the other thing, but we then have our 2 other profiles, though the hint recommends that we draw our guide curve first and then the sketch profiles. So we're going to want to get our radius of 15 guide curve in place, and then we can add in our arc slot sketch and our ellipse sketch on those 2 sort of other points. So middle sketch, top sketch, use the loft to loft the 3 profiles together, select the guide curve as a guide curve, and that should create our loft. And then we'll wrap it up with a dome, which is nicely and easily spelled out for us as an elliptical dome with an 8mm depth. So we're going to start with the puck at the bottom. I'm just going to use an extrude for this. You could do a revolve if you wanted to be special and fancy, but not really worth the extra effort. So we've got ourselves a circle. Might as well start it at the origin since that seems to make sense. And we can set our diameter to 50. And we ought to just be able to, yep, there we go. Cool. So we got that. Then we can extrude boss base. Since we're not actually going to be using the top plane for anything, it doesn't really matter how we set this up. I'm going to do a direction 1 blind extrude down at our 10 unit depth. Just because to me that makes a bit more sense, but it's not really going to change anything. Check mark. All right, next up we've got our sweep, and as we have been warned, we want to start with the helix. So to create a helix, we can go over to the curves bit and select our helix and spiral option. Then if we read our message, this says that we want to select a plane, planar face, or edge on which to sketch a circle to define our helix cross-section, or a sketch that contains a single circle. So we want our helix to start on this top face here, Control 8 to bring us normal to, and our helix's cross section would effectively be if we're looking at it from the top down, or just squished like we squished a spring. And we are given its diameter here. So it's got a diameter of 30 units. So we'll plug in our 30, and then when we exit our sketch, Control 7, so we're looking at our isometric, we can see that it brings us into the helix tool and shows us this. So the next important part is, what do we know about our helix? We are told a pitch and a height. So we'll go to height and pitch here. We know that our height is 20 units, our pitch is 10 units. Now we have a start angle and our handedness. So for this class, our start angle is always going to be 0 or a multiple of 90. So guess and check works well here. Based on the isometric, we can see that it looks like the tail of the snake starts sort of in the back. So 0 doesn't quite work right there, but if we plug in 180, we can see it does start in the back. Also, from our isometric, we can see that it sort of starts in the back and then goes to the right and curls up. So checking clockwise, counterclockwise, it looks like it does remain clockwise here. Check mark. So there is the first component of our composite curve. Next up, we need the radius of 5 arc. We can cross out our note there. So for that, first we need a reference plane. And whenever you're creating a sweep path, you always want to define your reference planes by first selecting the end of the previous curve and then selecting something else to help us define this. So based on our front view, we can see that we're given the dimension, the radius of 5, based on the front. So that tells us that when looking at it from the front, the arc is in true size and shape, meaning that the plane we are sketching it on needs to be parallel to the front plane. So we can select the front plane as our second reference and check mark. Now we'll open up a new sketch on the front plane, and we get just an arc. So I'm just going to draw an arc out in space, and then we'll define it off of the other geometry, because one thing that you've probably noticed when trying to do this is we can't just connect endpoint to endpoint with this. So we need to do something a little bit beyond that. So we want to select the endpoint in the current sketch and the edge of the previous thing. And then we can apply a pierce relation, and that connects our arc right to the end of the helix. Now we can start throwing some other stuff at it. So we know that it has a radius of 5. It looks to me like it goes up until it goes vertical, pretty much. And based on the tangent lines, so we get these sort of fainter dashed edges in the isometric, that tells us that each portion of the sweep is tangent to the previous portion. If there was a sharp edge in this, then we would not be able to make this assumption. But because we have these, or if this was a sharp edge, we would not be able to make this assumption. But because we get the fainter lines, we can safely assume that this arc is going to need to be tangent to the previous helix. And if it connects into something vertical and is tangent there, what we can do is create us a center line, set the center line to be vertical, and then apply another tangent between our arc and our center line. You could also set a horizontal relation between the center point of the arc and the endpoint. That would give us the same geometry, but this sort of center line and tangency thing clicks a little bit easier with me. So, and with some of the students I've talked with, so that's why we're doing it that way. But lots of ways to do the same thing. Exit sketch. So that is our first sketch, or the second portion of our composite curve. So then for the third bit, we see that we've got our arc is visible in section B. And section B, oh yeah, we can cross out our radius 5. Section B is given based on this cutting line. So what we know about that cutting line is it looks like it passes through, sort of right through this bit of the arc, so it goes right through the middle there. And it also passes right through the center of our or the center of our circle. So we can't define a plane with just 2 points, but we also know that this plane is, well, the entire plane shows up as a line in our top view. So we could use that to say, oh, well, this plane is also perpendicular to the top face of our object or the top plane. Or if we wanted to be slightly more efficient, we can also notice that because the plane goes through the middle of the circle, that tells us that the plane itself is going to need to be coincident with the center line of our cylinder. So a point in one view then would extend to a line, or a center point in the top view would extend to a center line in 3D geometry. So if we go over to our visibility options, we can then select View Temporary Axes to get access to this line here. And then if we go to our reference geometry, we can create a new plane using the endpoint of the previous sketch as our first reference, and that reference axis, or that temporary axis that we just brought in as our second, and check mark. Cool. So now we've got that, we can create ourselves a new sketch, Control 8. We know that this is an arc because, well, A, that's all we see, and B, it tells us that we've got the, does it mention it specifically that it's just arcs? It looks like it's just an arc, so we'll just draw an arc. And following the same thing I did last time, I'm going to draw it sort of out in space, and then we'll bring it in. So we're going to select the point in our current sketch and the edge of the previous sketch, apply ourselves a Pierce relation. Then we can apply a tangent between our current arc and the previous arc, which will take care of that. Then we can apply a smart dimension to define this as having a radius of 4, which almost but not quite fully defines our model. We still have the endpoint here. So let's cross out our R4. The other dimension we have that kind of references this at all is our 50-degree angle that we get in section B. So that's telling us that the end of the arc, sort of the perpendicular line, so sort of the anti-tangent, effectively, if we draw that in, it would be a center line that is coincident, and they don't have a perpendicular, but main moral here is that a line that is perpendicular to an arc is going to have to pass through its center point. So we can draw ourselves in a construction line like this, and we know the angle that this line makes with the horizontal is 50 degrees. So dimensioning from that to something horizontal, we can then plug in 50, and we get us a nice fully defined sketch. Exit sketch, cross out our dimension, and now we can stitch the 3 curves together. So for this, we'll go over to curves, third time's the charm, composite curve, and we can select our curves in order. So helix, small arc, smaller arc, check mark. And that then stitches all 3 of them into a single curve. And at this point, we can then use our swept boss base with the circular profile option with our diameter set to 8 and choose our arc. Check mark. And then that is going to generate for us a nice curl for our snake. All right, next up we've got our lofts. So the hint tells us that we wanted to start with a guide curve. So we see that that's the radius 15 arc, and we can see the radius 15 in the same view that we had the radius of 4. So that tells us that we don't actually need to create a new plane for that. We can just use the reference plane that we used to create that radius 4 arc. So we're going to open up a new sketch on that reference plane, and we'll draw us in an arc, something like that-ish. Now we can go about defining it. So the radius of 15, I'll plug that in first, goes along the inside of the hood of the snake. So that tells us that the start point for this arc is going to need to connect in kind of with the top arc there of our sweep. So we can take the end point and our edge and apply us a pierce relation, and that gets that in place. Similar, it looks pretty smooth where it transitions from the circle to the inside. We do have a solid line separating the sweep and the guide curve, or the sweep and the loft in our isometric, but here that looks pretty tangent. And the other hint that we've got is the 50-degree angle. The leader for that passes through the center point for this arc. So if we wanted to, we could go into our other sketch. So we'll show that there. Then we can take the end or the center point of our current sketch and the construction line we drew earlier and apply a coincident, which does define our geometry, or pretty much following the same geometric principles, if we take our arc and the sort of silhouette edge and apply a tangent, that will define the same thing. So you can pick one or the other, or in this case, both. And because the rules are saying the same thing, they don't conflict, so SolidWorks will allow it. All right, next up, we've got an 80-degree angle. And we can see this goes from the horizontal to sort of the end of the sweep, or the end of the guide curve. So I'm going to use the same basic trick we did before. We're going to draw us a construction line that goes from the end point and passes into the center of our arc. And this one, yeah, the hood sort of goes up and over a little bit. So the 80 is being measured there. Yeah. So we can define our dimension between those two, plug in the 80, yep, and that then fully defines our sketch. So we'll exit sketch. I'm going to hide the previous one since we don't need that anymore. And at this point, we can go about creating our other two profiles. So I'm going to do the arc slot first, since that's the next one that's going to connect in. And for this, we're shown all of the dimensions in a section view, and the section view is taken based off of a cut drawn 45 units up from the base of our object. So for that, I'm going to create us a reference plane that is going to be an offset plane from that top surface. So up 45 units, check mark. Then we can create a new sketch. And I'm going to hide the other reference planes so we can see the current sketch better. There we go. All right, so we need a center point arc slot or a 3-point, either one works fine. We can see the center mark is somewhere around there, so I'm just going to put that around there-ish. Then looks something like that, and that. Alrighty, so at this point we've got a couple more things to define. So let's start throwing some numbers at it. We know that the large arc on the outer edge, this has a radius of 40. We know that the two smaller arcs each have a radius of 2. We know that the distance from end to end of our center line there is 30 units. So now we just need something to define its location and something to define its orientation. And for these, we can see, so we've used our 30, we used the 40, we used the 2. We see we also have this sort of 90-degree reference dimension that we can sort of use, and that defines the line that's drawn in there, so let's add that in just for consistency. That defines that line as being perpendicular to the cutting line that passes through the center of our object. So that cutting line is also pretty much going to be plane 2, so we can show plane 2 there. And we know that the center point for our arc lives on plane 2, so we'll apply a coincident there. And we know that the center of the arc, so there's the center point of the arc, and then there's this center of the slot, also lies on that plane. So now it is almost fully defined. The last bit that we need is something to relate our arc or our arc to the guide curve. So if we hover around the middle of this arc, we can get access to its midpoint, hold down our shift key and select the arc itself of the guide curve, and we can apply a pierce relation to set that up at that specific point in space. Cool. So now the guide curve touches the profile of the loft, which is generally something you want to aim for. So we'll exit sketch, and then we can create the next sketch for our ellipse all the way at the end. So for that, we can see that our cutting line sort of goes through and touches the end of our guide curve, and it passes through the center of our arc. The other thing that we can note, one thing that we've seen several times before today, several times before in this example, is that when you've got something that sort of passes through the center of an arc, and here we're seeing it in this perspective, what that effectively tells us is that this plane is going to be perpendicular to the arc at that point. So I'm going to create us a new reference plane that is defined based off of the end of the sweep and the end of the guide curve and perpendicular to the guide curve itself. Check mark. Now we need to be a little careful with this sketch, because if we take a look at it in the normal perspective, it is very slightly cockeyed to the rest of the model. So we can't use the horizontal and vertical relations that are built in. We're going to need to define this relative to the geometry that we already have. Otherwise, the head is going to be tilted very slightly. So we're going to draw in our circle, or our ellipse, sorry. And we know that with this ellipse, the bottom point of it is going to come into contact with the end of our guide curve. And if we want it to be aligned, like we see there, we also want the top point to be coincident with the guide curve, or coincident with the extension of the guide curve. So now that we have that oriented correctly, we know that the distance between the top and bottom of our ellipse, so this is the distance between them, not the height, but the distance, is 8 units. And the width of our ellipse, so not the horizontal width, but the actual Euclidean distance between these two, is 10 units. So you want to make sure that your dimensions are aligned with our shape, not with the coordinate system. Because if they're aligned with the coordinate system, then they're going to be very slightly off, which is probably why a couple of students were having difficulties where you were off by like 1/100th of a gram. So we'll have to double check those and see. But that completes that sketch there. So now that we have that done, we can go to Lofted Boss Base. We want to loft this profile to this profile to that profile. And when we apply our guide curve, let's hit our check mark. Yeah, there we go. It will fully complete our Cobra's hood. So last few cleanup bits, we've got the dome. Can never remember where the dome is, so we're just going to type dome into our search bar. We know that it is a dome with a distance of 8 based off of this surface, and it's elliptical, so that ensures that the entire dome does not expand beyond the boundaries. Check mark. And then we can set our material. So we've got a silicon rubber. So we're going to edit material. So silicon rubber, apply that. And if we double check our mass, you can see we are 42.84. Huh. Okay. This may be a different problem then. Let me double check. All right, so this could be an issue where I was a little sloppy with these dimensions. Come on. I'm going to try add some center lines, and then if we measure the center lines, they might behave a little nicer. There we go. So we want the actual distance to be 10. We want the height to be 8. Now if we go check our model, this property is 42.84. The other thing that could be causing problems here is maybe on the answer key I didn't quite. That would just increase the mass, wouldn't it? Oh, it's such a small difference that it doesn't change anything. The other problem might be with all of that talk I did about trying to get the orientation correct. Did I screw that up on the base model? All right, even that is not causing a difference. So here we run into one of the many quirks of SolidWorks, and that is that uh, sometimes, even if your model is created through a perfectly legal and reasonable means, um, it can still cause issues because the method that it uses to calculate volumes. So let's see, this should be 8. This should be 10. But the method it uses to calculate the volume of something can be very slightly different from machine to machine and from install to install. Yes, that's still 42.84. So because of that, you can end up with some very slight mass differences. The other thing that I'm thinking could cause problems is if I try merging the tangent faces. Nope. But in any case, we followed all the correct modeling principles to get here. So this would be the correct answer. Um, the other problem could be a typo. I'll double check that. But yeah, so in any case, that's the methods that you would want to use to actually model this component. I'm going to double check some stuff and then we will start recording for problem 4. So thank you, and let's take a look at the Pokeball.